So it's a great pleasure to start the second session for this workshop. And we have the keynote lecture by Professor Jerry Moloney. So Jerry is a pioneer of photonics and is professor at the University of Arizona, and among other things, has been elected fellow of the Optical Society and was awarded by the Von Humboldt Prize for Physics in 2005. Please, Jerry, the floor is all yours.
Thank you very much, Matteo. And I'd like to thank the organizers for inviting me to give this presentation. And of course, Matteo Clarici and Lucia Caspani for being wonderful hosts to my wife and I and our little dog. We've had a very enjoyable week here in Como. And I discovered I was driving in the wrong directions on the one-way streets, but so far nobody's put me in jail, so hopefully I'm okay. So what I'd like to do is, I am not going to talk about this topic, but I think it's very important to put that picture up there because back in the early 2000s, the group here at the Insubria University had an absolutely outstanding laboratory, and they did some amazing experiments. And this beautiful picture was Daniele Faccio actually, I think, won the Optics Photonic News magazine. He won the prize for the best picture with this photograph. This is real data. And we were very fortunate to collaborate with Paolo, obviously the Trapani, and obviously with Daniele Faccio. And at Arizona, we did many of the theory and experiment studies. And not experiment simulations, I should say, numerical experiments. So let's see if I can get this guy going. Yeah. Okay, so I'm not going to talk about this topic, but I was trying to make up my mind can people hear me? Good, okay. I was going to try to make up my mind what I would like to talk about, and I thought this is a topic that maybe is not terribly familiar. Hopefully, people may learn something. It's microscopic physics driven design of three-dimensional and quasi-two-dimensional semiconductor materials. And the idea here is that I hope I can convince you that many body interactions in these physical systems can profoundly change their optical properties. So I'd like also to dedicate the talk to a colleague, the late Stefan Koch, who's a colleague and friend. This book here, in fact, is the Bible on this whole topic. So, yes, this picture, because I'm in Italy, people have probably heard this story, but this is, of course, a very famous Italian physicist, Enrico Fermi. And I think he was doing an experiment on meson proton scattering. And this is a story by Freeman Dyson, who, of course, was also, at the time, a very young theorist, but of course he became a very famous theorist. And Freeman Dyson basically was modeling Fermi's experiment. So he was very excited. He came into Fermi's office and said, how many arbitrary parameters? Fermi asked him, how many arbitrary parameters did you use in your calculation? And after a while, Freeman Dyson said 4. And then Fermi said, I remember my friend Johnny von Neumann used to say, with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. And this was a big, obviously, Freeman Dyson left in a hurry and, in fact, stopped modeling that experiment. But the moral of the story, obviously, is, in physics, you have to, the systems are complex, you have to parameterize. But I guess the moral of the story here is that while you need some parameterization, less is better. And this is really what this talk is kind of about. So, okay, so I'm going to give an outline. So I'll give some background and history. I think I'll talk about a derivation of these semiconductor block equations. Even though I'm a theorist, I list some of the experimental experiments that have been actually carried out with using these microscopic designs of these semiconductor lasers. And then these material systems, these quasi-2D These are graphene-like systems, but they've got a finite band gap, and they actually have some really dramatic and very profound changes relative to 3D semiconductors. Then at the very end, I'll briefly talk about this ultra-fast high-field physics, and it relates to topological materials. Okay, so the first thing is I call this the dephasing time dilemma. Everybody here knows what the T2 dephasing time is. And in fact, I just wrote the two-level optical block equations because I'm sure everybody's totally familiar with them. But the issue here is this T2 dephasing time. In fact, both of these dephasing times are not very meaningful quantities when you look at solid-state interactions. But the T2 dephasing time in particular, even historically, it immediately caused a problem just in terms of being able to compute the line shape, the proper line shape in a semiconductor laser. And currently, the T2 dephasing is used as a free fit parameter. When theorists do high harmonic generation and strong field physics, they use it as an adjustable parameter to fit the theory to the experiment. So I hope I can very quickly convince you as to why this is an issue, and also T1 in fact, but T2 in particular. So this is of course just an overview. This is the direct band gap of a semiconductor solid. Here, this could be a three-dimensional or a 2D quantum well. This is just an example of gallium arsenide. But all of the interesting physics occurs at this gamma point. So if your photon energy is close to the gap, the band gap, then you're dealing with resonance, absorption, or you build a laser. But there's another regime of operation where you're highly detuned with a very high field terahertz pulse, short terahertz pulse, and this is the non-perturbative region, where you can actually, your photons are much, much shorter than the gap, and you can generate very extreme high harmonics in the solid state. In these materials, the transitions are, of course, at this gamma point. This is the symmetry point. Another very important concept is obviously when you excite an electron from the valence band to the conduction band, you create an electron-hole pair. This is a hydrogenic system. So essentially the bound states of that hydrogenic system are so-called excitons. And the mass here, of course, is the actual local band curvature in the vicinity of this gamma point. Now, in conventional semiconductors, you have to go to very low temperatures to see excitons, these features. This is the 4 degrees Kelvin, for example. And if you go to room temperature, they are completely consumed by the absorption continuum. As I'll show later on in these quasi-2D materials, the excitons become the dominant feature, which is really interesting. So this is the first problem with the T2. So if you compute the gain, this is negative absorption for a semiconductor, using some fixed dephasing time, yes, you get gain, but below the band gap, you get this constant absorption, and that's non-physical. Makes no sense. If you do the calculation correctly, I'll show this on the next slide, the gain actually happens to be much larger, but of course it asymptotes to zero absorption below the band gap. So that was the very first situation, as I point out, where T2 didn't make sense. So here's how to fix the time shape problem. So this guy here is in the semiconductor block equations, which I'll get to. The correlations, I'd like to be able to write this correlation time as a polarization times a 1 over T2. That would be in the optical block equations. So in effect, if this guy here was the only contribution to the microscopic polarization term here in green, I could write this whole term in green. It's a highly nonlinear interaction. You can write this in green as 1 over T2. But of course, that 1 over T2 will also, you could say, could depend on the momentum K. This is the momentum of the carriers. Now, of course, this gives the wrong line shape. So if you still retain terms linear in the polarization, this guy here is still linear in the polarization, but it involves non-diagonal. This guy here is diagonal, K to K. If you're coupling to other relative momentum, these terms combined give that correct line shape function. So this is something that is not representable as a T2 constant or a T2 as a function of momentum. But this is not the whole story. The microscopic polarization has additional terms which involve triple products of these microscopic polarizations. This term is not relevant for resonant interactions, but for non-resonant, for these terahertz, highly detuned interactions, these non-equilibrium polarizations play a significant role, and this is still an open problem. It hasn't really been, these equations haven't been solved yet. Okay, so I'm sure all of you, if you ever meet people in a social setting and they say, well, what you do is really interesting, but is it useful? I think I can hopefully convince you that microscopic theory here is actually quite useful. So what happens if you're going to grow a material to build a semiconductor laser, the grower obviously has to, typically it's a very costly, time-consuming operation. So what you'd like to do is you grow a calibration sample. You want to make sure you've got the quantum wells correct before you go and grow the entire system. So the only optical, there's lots of ways of lots of diagnostics at this level, but at the calibration stage, the only optical diagnostic is to measure the so-called photoluminescence from the sample. So here's a little example. I call it luminescence analysis. This actually is a sample with 3 quantum wells, indium gallium arsenide on gallium arsenide substrate. The nominal composition that the grower puts in is a 5 nanometer well, 80% gallium, 20% indium. And then, of course, what you do in the experiment is you use different these are weak fields, low power fields. You measure the luminescence from that sample. That's a function of increasing illumination. The theory doesn't really know anything directly about the external power of the laser. So all the theory knows is the density, carrier densities within the quantum wells. They determine the luminescence. So what do you do from the theory perspective is you run a whole series of densities in the hope that you're going to cover this range of illumination powers. And when you do that, you get these light red curves. Obviously, these theoretic curves are narrower than the measured ones, but this assumes a perfect and ideal crystal. The theory assumes a perfect crystal, and even with very high quality growth, there's always some degree of inhomogeneity. So one will have to broaden these lines, but this broadening is minor. But the major problem here is the offset, the shift. So in fact, in this case, if you would simply reduce the indium from 20% composition to 19, all of these lines line up with one another. And at this point, you need no more adjustment. What we're now going to do is we're going to increment the gain, the carrier density to go from absorption to gain. And when we compute, oops, sorry, this is too fast. Here we go. There. Boy, this guy's, he doesn't like it, right? Don't touch. Okay. So basically, these continuous curves are the computed gain. And incidentally, this experiment was done after the calculation of the gain. So this is an unusual example where the experiment verifies the theory, which we theorists are often told, here's some experimental data, explain it. This is actually, so this is a highly predictive theory at this level. Now, of course, it's not the end. When you design a laser, you also have to take into account the intrinsic losses. This is called the loss current. And this is a famous law called the ABC law. It says the intrinsic losses in a semiconductor could come from defects, defect recombination, spontaneous emission. And spontaneous emission here, you need an electron in the hole to create a photon. So the n squared dependence on carriers makes sense. And then, of course, you've got these OJ processes. So this is an established design formula for actually computing the loss currents in the laser. Typically, high quality growth defect concentration is very low. And in fact, the theory cannot account for it. But we can actually solve the so-called quantum luminescence equations, which I'll get to later. We can actually solve for the microscopically for the spontaneous emission and for these Auger processes. And when we do that, this is some examples for different quantum wells. This is the spontaneous emission. So if you divide the spontaneous emission by n, goes with n squared, expect a linear function. And these are actually microscopically computed at different temperatures, the heavy curves. The circles here are the point at which the laser turns on. So you find actually that the agreement is very good at very low densities, but where the laser operates at high densities, you get these huge deviations from this phenomenological law. Likewise, the same with the Auger losses. Here you divide by n squared to make them linear functions, and again you find these very strong departures. Okay, so now, yeah, and then of course, fortunately, there was experimental data that we could actually verify against. So this is actually a series of measurements of the threshold current for different quantum wells, and the dotted lines of the experiment. The red is the spontaneous, the blue is the Auger, and Auger processes at high temperatures are by far much larger than the actual spontaneous. So the idea is that when you have all of these pieces together in the microscopic theory, you can actually come up with a tool to design. It's called an epitaxial design tool that you can actually use to design laser systems. Okay, so now I'm going to briefly talk about the many-body theory, the semiconductor block equations. So here, let's see. So again, this is a second level of second quantization. The zeroth order Hamiltonian, of course, is just the energies in the conduction band and valence band, and these are typically extracted from density functional theory. These are single body band structure, and of course, these are the familiar creation and annihilation operators for the appropriate particles. It could be an electron or a hole, for example. The interaction Hamiltonian. This term here again should look very familiar. It's essentially dipole coupling between conduction valence band, which you see in the two-level atom. And this is, of course, here is the microscopic polarization. This product here. This term here is certainly not. It's not there in the two-level system. This actually plays a big role when you're dealing with highly tuned high field in the region of high field physics. This gradient term here, momentum, with respect to momentum, it's the so-called gives rise to the intraband current, which accelerates carriers across the bands. And in the higher order correlations, this is the lowest level at which these Coulomb interactions, this is the screen Coulomb potential, and involves the spore operator expansion. So as I said, when you're dealing with resonant interactions, you don't have to worry about this intraband current, but it plays a very significant role. It's related to vary curvatures and vary phases, etc. when you go to these highly detuned non-perturbative systems. So basically when you, this likes to jump slides for some reason. So now if you just take the total Hamiltonian in the Heisenberg equations of motion, you can derive equations of evolution. This involves two operators. I haven't put any subscripts or superscripts on here. This could represent populations of individual states, microscopic populations, or polarizations between bands. If you want to determine the equation of motion for this A adjoint A term, for example, it couples to four operator products. Then if you plug in four operator products, of course, then that couples to four into six operators. So you get this infinite hierarchy of equations in this many-body system. And then there are systematic methods to truncate those equations. But essentially what you have to do is with these higher order products, every time you manipulate, reorder, you need to reorder the products in factor such that each bilinear product represents some physically measurable quantity. It could be a population or a polarization. So the way you go through this is for graduate students, it's very tedious. Every time you manipulate these pairs, these operator pairs, if they're fermions, which they're in this case, you have to use the anti-commutation relations. But we'll also couple to phonons and to photons. So these can be, then you would employ so-called commutation relations. So these are the semiconductor block equations here, Maxwell semiconductor block. And they look very much like the two-level atom equations. This, in fact, is the inversion, the population inversion. And here is the correlation. I showed you already the expression of the microscopic polarization. It's quite complicated. And these are the individual populations, again, as a function of carrier momentum. And we're looking at the induced polarization, the interband polarization, essentially between these two states. So at this level, you already see the influence of many-body effects. So this is the Rabi frequency. The usual Rabi frequency, of course, is the bare two-level system that consists of a dipole matrix times the field. But now you have these Coulomb renormalizations. Likewise, the energies are renormalized. And of course, whenever you excite a semiconductor, you always get a very large band gap reduction. And that's because, again, of this renormalization of the bands. These are the, I showed you already the microscopic polarizations. These are the correlation terms, again, involving Coulomb. These are the Coulomb potentials. This is an energy conservation term. And these, again, as I said, are highly nonlinear. This is for electron, and you have hole, the equivalent one for the hole dynamics. And also you have to couple the phonons, so you have a similar equation where the carrier is coupled to the phonons, where the system relaxes to the lattice temperature, essentially. Okay, so now let me quickly go through some applications. And so we have the microscopic design, and I showed you how it works for a simple few quantum wells on the substrate. This is to contrast what I'm going to talk about. This 10-disk solid-state laser has been used by Trump. This is a multi-kilowatt source, which was used recently for that laser lightning demonstration not far from here, actually, in the mountains of Switzerland. This laser has some advantages. Very thin. The semiconductor, the solid-state gain chip is this tiny little black spot here sitting in the center. And then you have a big parabolic mirror. To get this guy to laze, you have to do multiple passes through the chip to go above threshold to actually laze. But of course, its advantages, as I said, it's a multi-kilowatt source, very, very high power laser source. So one of the disadvantages of multiple pass absorption. These are dopants, so you have to stabilize the pump. They're optically pumped, so you have to make sure your pump is aligned with the absorption. And also they're wavelength specific. If you change dopants, the wavelengths change. By contrast, this would be what I call a thin semiconductor disk laser. So now what we have here, it's 6 to 10 microns. Take the whole structure, but it's got a big DBR, distributed Bragg reflector at the back. And in here, it's got this periodic stack of quantities. And these are arranged at the antinodes. This is a little microcavity. It's about a micron thick, the actual microcavity. So it's the fabric cavity. So when you pump this guy, you can actually optically pump it in a single pass. You don't need this multiple pass configuration. But also, because of the microcavity, you can actually resonantly enhance the gain. So in addition to the pure gain you get from going through the quantum wells, you get a very strongly enhanced gain. These are incredibly quiet, low noise lasers because the light is going through the quantum wells rather than the longer quantum wells, which it would do in a standard edge emitting laser, for example. So these are just some experiments, just showing again. So these gain chips were designed with the microscopic theory. These are input-output curves, pump versus output power. So these lasers turn on and they suddenly turn off very quickly. And of course, again, you get up, this was 15 years ago, up to 20 watts. We got up to 100 watts out of a single chip. Dissecting the chip. So as I mentioned, you can measure, let me just go back here quickly. Yeah, I put this in here and I should have remembered it. You can measure the photoluminescence from the edge. It's called edge photoluminescence. This is the photoluminescence I mentioned earlier. But you can also measure the photoluminescence through the surface, but then you have to go through this complicated structure. So here, for example, this green curve is the edge photoluminescence. That would be the characteristic of a single quantum well. But now you have to get the surface luminescence through the surface, you have to include the filter function for that whole structure, Bragg mirror, and refractive index jump at the other side. When you convolve these two, you get this surface luminescence. And again, the theory is the red, and the experiment is the black curve. God, this guy does like to jump. Oh no, it's okay. No. Just yell at me if I'm taking too long. Because we got a Bragg mirror, This guy is going to have a finite reflection stop band. So here in this picture, the little dip here is that because you've got the quantum wells, you're getting up. The absorption of the quantum wells creates a little dip in the Bragg reflection. And he designed this laser so that at room temperature, the absorption peak is at lower wavelengths than the cavity resonance. The cavity, of course, has its own resonance. When you heat this chip up, when you pump this laser, it gets hotter. So all we're going to do here is going to take this passive structure and just heat it up. If you heat the structure up, you find that the cavity resonance goes very slowly. It just depends on the thermal refractive index of the semiconductor materials. But the absorption peak is much faster. So when the absorption peak catches up with the cavity resonance, you get deep absorption. And then if you heat it further, the absorption peak passes the resonance, and the absorption shuts off. And that's effectively what you're seeing here from the gain picture. You get it's heating up as you're pumping it, and then of course it suddenly switches off at some critical temperature. So the idea here is you've got some like closed loop way of you have to take into account thermal. You can actually design these in principle, design them and then ship them off to the grower to grow the particular structures. How am I doing? Lots of time. I put this app on my phone, but I don't know how it works. Thank you. Usually you operate these devices in a V cavity, not a linear cavity. The nice thing about a V cavity is you can put optical elements into the cavity. The semiconductor gain chip is sitting here, it's on a heat sink. And so now I'm just going to show you, we can redesign this for different wavelengths. This guy here was designed to emit at 1040 nanometers. You can obviously design it for different wavelengths. That's the nice thing about these semiconductors. And you can put here an LBO nonlinear crystal in the cavity, down convert to 488 nanometers, and then further down to 244. So you can generate, these are pretty high, you might get hundreds of milliwatts in the UV. These are all CW. We even went ahead and designed the gain chip to laser 1178 nanometers, which if you divide by 2 is the famous sodium D line. And in fact, we back then proposed this as what we call it a guide star in a shoebox, because these sodium lines are exactly the frequencies you need for if you put guide stars on telescopes, for example. And I do know there are some projects actually trying to build these devices at the moment. You need only about 10 watts apparently to be able to make a guide star. These will be very inexpensive guide stars relative to the multi-million-dollar businesses. Another application, again, by just putting a very thin edge on in the cavity, you're forced to go 2 wavelengths. The wavelength separation is around 3 nanometers, which in the terahertz corresponds to about 1.9 terahertz. So we were able to build a room temperature terahertz, tunable terahertz source. This was 15 years ago. A few milliwatt tunable terahertz source. And then, of course, you can also add receptive absorber there and make this thing pulse. So you can actually create a mode-locked laser. And here's an example of what we call a colliding pulse mode-locked laser, which we built actually in Tucson. Alexander Laurent built this system. It's a very interesting system. It's a ring cavity. So in fact, you get mode-locked pulse trains going in opposite directions, passing through one another around this ring cavity. And in fact, when they exit the cavity, they come out as 2 separate beams. So you can actually, beams of, I should say, pulse trains. So you can actually you can play games of trying to correlate these pulse trains, et cetera, et cetera. And we actually, at this experiment, we generated about 95 femtosecond mode-locked pulse train, which I think it's still, Ursula Keller did a little faster, but she cheated a little bit. I can say that because Ursula's not. They actually compressed their pulse external to the cavity, whereas this pulse was actually compressed in the cavity. Here's an example. Again, this is our chip, this little V cavity. But we at 230 nanometers, we run through ytterbium amplifiers, get 8 to 10 watts at 1030. We split off at 1 watt, take it through a silicon nitride waveguide. It generates a supercontinuum, and we can actually pick out 1.5 micron. and combine it with a 30 nanometer and generate a 3 micron mode locked, mid-infrared mode locked pulse train. And this is offset free because we have a common source. Usually with mode locking, you have to this offset frequency you have to determine. It's complicated. Here, because you've got a common source mixing both frequencies, it's offset free. You don't have to worry about those issues. Here's an example of a measurement. It's called the VIPA, Virtual Image Phase Array Spectrometer. It's essentially a tilted echelon where you, with a very high reflectivity surface, you couple the light into it, it disperses the pulse trains, and then you also use a grating to disperse in the other dimension. So what you're seeing here, every little bright spot is separated about 1.6 gigahertz, which is a reference of the laser. This is an empty cavity. If you put methane gas in the cavity, you get these dark regions where the methane is absorbed. And then you get the graduate student to unfold this whole thing. It's the black curve, and this is the red curve is the Hytran database for methane. And we actually did this also where we had the gas filling that you could dynamically modify the buildup of these gases. So this again was a proof of principle, basically a source for it's a mid-infrared imaging system. Okay. This thing is crazy. Okay. Sorry. Okay. No, I don't know why. This thing just. Okay, here we go. Thank you. Transition metal dichalconides. So these things are essentially, these are blue metal atoms. They might be molybdenum, tungsten atoms, for example, the blue guys. If you replace each of these blue guys by a carbon atom, you'd have graphene. But of course, graphene has 0 band gap. So these materials do have a finite band gap. They're covalently bonded to, say, sulfur, selenium, etc., etc. So these TMDC structures, a monolayer of these structures has a direct gap, so you can actually make a laser out of them. They're proposed for micro LEDs. Spintronics, which I'll mention a bit later on, and Valitronics. So these guys, if you look at the band structure, this would be the single particle band structure for these. This is the conduction band, valence band. And if you take this cut, this would be irreducible Brion zone. Fold it over 6 times, you can cover the full Brion zone. If you track from gamma to draw through this line, you can actually hold the actual band, a picture of the band structure. And here, unlike the standard laser semiconductor, which typically lays at the gamma point, here you find these 2 direct gaps, what's called K, and the other K prime point. And the difference between K and K prime, the red and the blue, is you have a spin up and spin down state. So you can actually excite the spin up or spin down with different circularly polarized beams, for example. So this is why they use this term spintronics. You can actually control the individual spins. Here we go. Okay, so now again, the inputs we need to the many-body. This is still at this is the single particle level. We need those picture energies, and essentially with those plots I showed you, the wave functions. This Coulomb form factor allows for the fact that there's a finite extension in the z direction. It's not a strictly 2-dimensional material. Dipole matrix elements, and you need all these as input. And then you can write down these semiconductor Dirac block equations. And here they look very much like these regular semiconductor block equations, inversion, battery frequency. These are the polarization population. But now this is called the Hartree fault, the lowest that you bring in many-body effects. These renormalized energies and fields are much more complicated. And they involve these many-body interactions. These are there. These terms here these are so-called pair correlations. They can have 2 pairs of electrons or holes correlated. These are Auger-like terms. 3 electrons, 3 holes, 1 electron. This is typically the process you'd see you associate with an Auger. So again, the renal, all of these things appear at higher up in the hierarchy when you're dealing with the standard semiconductor. They now appear at lowest order. And just to illustrate how dramatic these TNVC materials, how they respond, if you place them on different substrates. So molybdenum disulfide on silicon these are the excitons. Um, and these excitons now are huge. Remember, the excitons in the standard semiconductor, you got to go to degrees Kelvin, a few degrees Kelvin to see them. If you put it on gold, you get this massive shift in these features. And then, I guess, here we go. Okay, again, this is, again, because we have the microscopic physics here under control, we can compute the absorption and gain of these materials. But again, here you can see the so here the excitons completely swamp the background absorption, whereas before the background absorption consumed the excitons and you could only see them at a few degrees Kelvin. Here at room temperatures, these excitons are huge and they're incredibly sensitive to environment. So they can shift all over the place, which means you can make some interesting sensors. They're proposing making wearable sensors with these excitons, for example. And here are some examples of these exciton features. Monolayer disulfide on silicon. And then if you can just blow up the increasing characteristics. You blow up this part quickly, you can get off to the gain. And they've been demonstrated to actually run as lasers. And then this is molybdenum disulfide on silicon. And again, of course, you get a whole host of tungsten disulfide on silicon and tungsten disulfide on silicon. So all of these materials have these huge exciton features, which, as I said, are incredibly sensitive to environmental. And so they can actually, they're being proposed as wearable sensors. It's just thin materials. You could make a fashionable outfit you could wear, and you could walk around and act as a sensor. Okay, so I hadn't mentioned the luminescence equations. I showed you pictures of luminescence. These are the semiconductor luminescence equations. So here, of course, in addition to quantizing the material, you have to quantize the field, the classical field. So this thing here is an expectation value. This is a photon creation operator times the microscopic polarization. That'll be your A adjoint A operator. So you have to derive the equation of motion for they're called photon-assisted polarizations for these systems. And this equation has, of course, it's got the Coulomb interactions, and also these are high-order correlations I'm not going to talk about. But it just shows how dramatic these things are. If you turn off the Coulomb and these correlations, the photoluminescence happens at 2.4 electron volts. And that would be the bare band gap. That would be your single particle system. Once you turn on the Coulomb, you get this huge shift over 0.500 milli-electron volts. You get a huge downshift in the absorption peak. And then if you turn on these Coulomb correlations, which involve correlations between the excitons, you get this final picture here. So these materials, and in fact, this book, this article by Kuhn et al. Actually goes into great detail on the derivation of the system equations. And okay, so the Auger, I just want to very quickly say that, remember we have this Auger process, the phenomenological model said there was a constant times n cubed. Let me just go on to this extra picture. Essentially, this is a constant, C, as a function of density. That's not constant n, the constant. Because of the huge band gap, the multiple band structure, because these bands are shifted so dramatically, this thing is not even remotely a constant. It's a much more, it's a very, very non-trivial behavior. And if you dump carriers into, this is actually, again, that irreducible representation of the Brillon zone. If you dump carriers randomly into the system, they go through these many-body scatterings. So it takes on the order of 1 femtosecond for these to drop down to the local, what you call a local equilibrium. but then much slower. They're going to get trapped in some of these states, which are not the lowest energetic states. And eventually, with the phonons, it takes about a picosecond for them to cool down, and then end up in the K primed points, which would represent the minimum band gap. That's just a summary. So here again is another illustration. Now this is again a system driven with a very strong field. And you were looking at high harmonic generation in this system. If you turn off the Coulomb, this is your conventional band structure. You get first band, the second band, you get the broad absorption feature. Turn on the Coulomb, you get these huge excitons. And now if you actually generate, if you compute the high harmonics of the system driven with a short pulse, you find again, not surprisingly, around this region here, you get huge enhancement or two actually enhancements to the higher harmonics relative to the usual single particle calculation. This just shows blow up of this is again a terahertz field. We take just half a cycle, and what this shows in fact is in these materials at each of these points on half the cycle, the carriers, this is the entire band, gamma, right back to gamma, sigma, K brand. The carriers are actually sloshed back and forth. They're driven across the entire brain zone. So this is where these intraband currents, the huge one, that gradient of K term that I said wasn't important for resonant interaction. And let me, I don't want to show, that's polarization, lots of terms. I'm going to quickly wrap up. Yeah? 5? Or that's fine, or that's fine. I'm going to briefly talk about these, again, right now it's a very hot topic, high field physics, non-perturbable high harmonic generation, for example, in solid state materials. And of course, one of the big problems here is one has to have these so-called gauge invariant solvers, because if you just take your dipole matrix elements from DFT, the phases of each dipole are completely random from K point to K point. So you have to include that these are smooth, these dipoles are actually smooth. So Miroslav Kolosek, who's a colleague of mine, actually developed this it's a gauge independent solver because it doesn't directly solve the semiconductor block equations. It just directly evolves the density matrix. So here, this is like a unitary matrix that you just advance with classic quantum mechanics. So here you don't actually expressly write down any dipole matrix elements. You don't have to worry about phases. He just advances the, this is in the velocity gauge. K sub t here is K minus the vector field. And you can also write it in the usual, I guess, the dipole gauge here. But again, you can make these gauge shift vector. This is the difference of the so-called between the various connections. Gauge invariance. So then you can actually use either of these approaches to compute higher harmonic generations and not worry about the these issues of these. In fact, in topological materials, you can get these non-zero churn numbers. So you get a discontinuous jump in these phases. And within this either of these frameworks, you can actually take care of this. Here's an example. This model, QWZ model. In the topological phase, the high harmonic generation is crystal directions. You go to the crystal phase. I'm just going to, gap graphene. This again is a concocted model. It's a two-band model, but everybody uses it because it's kind of easier to study. But the nice thing about gap graphene is the Hamiltonian terms of Pauli matrices and this parameter B. You can open up, as I said, graphene, of course, has zero band gap. But if you vary this third component, you can open up the gap. This is kind of to me, it's an artificial procedure, but at least you can do it. And you can work with a smooth gauge. And we actually just very last few days I got the data. This is actually the absorption band of this gap graphene and single bond. Then we know that when you turn on the many bonds, you get this huge shift and you get this big exciton. appearing at the front end. And here we compute the high harmonics, again at the single particle level, and then at the many particle level. And there's a huge enhancement. Most of the community uses single particle. They're now starting to talk about many particle. I think this is a bit of an artificial system because of this finite absorption band. But the reason why these are so large compared to the single particle, I'm convinced that this guy has shifted to such an extent that you're essentially generating harmonics in the transparent region of the system. But there's no doubt that many body effects are unavoidable in all of these systems, even at the most central base of development. And I believe now the community is starting to realize this. And so one thing, basically this is essentially my wrap-up slide. So these many body effects are pronounced in these 2D materials, not so much in 3D. The dephasing of the polarization, I mentioned, is well established in resonant interactions, but still an open problem to compute that full system. We still haven't managed to compute it. It certainly is not a dephasing time. It's some very, very complicated function. And as I said, in 3D solids, these exotonic effects are so weak that I believe that it doesn't have a big influence if you go from single body to multiple. Thank you so much for your time, and I have no idea how much time I have. Over a glass of wine.
Oh, with a glass of wine
I had a
later.
glass of wine presenting.
Okay. But if there are urgent questions, please go ahead now. I have some curiosity, but I'd rather ask.
There's no urgent question. It's kind of very different, I guess. Oh yeah, sure.
Yes, please.
Very nice, inspiring talk. Concerning this non-controvertive order one, my question is, so I'm an experimentalist performing this kind of experiment, which are really challenging. And our perspective is we don't know how far we can go in understanding the properties of the material, particularly excitodynamics and in this kind of 2D materials from high order harmonics. Do you think we stand a chance, considering from the theory point of view, that we can really extract some information? Yeah. Yeah. Yeah.
I don't.
I mean, my feeling is that you cannot really avoid taking into account multi-electron facts in all these experiments. And my understanding from your talk is that this feeling is kind of correct. Okay. See how far we can go with this.
Thank you again.